Hello, everyone, and welcome to this session of our global webinar series. My name is Wilmer Companioni, and I lead the technical marketing team at KEMET. And today I'll be playing a little bit of double duty as both your host and your presenter. This webinar, we're going to try to do something a little bit different. We're going to try and take a look at the most recent product launches at KEMET. As you can imagine, pandemic or not, we all still have businesses to run and things to do. And that's no different for KEMET. So in the past quarter, we've launched a series of products that are meant to address a number of different design challenges in the industry. And I'm going to try to stay away from too much superficial marketing stuff when I talk about these launches. And I want to get into the what, the why, and the where of each of these product launches and these introductions that we've made here in the last quarter. So with that, let's get into our agenda a little bit. So in the past quarter, some of the primary launches that we've completed are the ones showing on the screen. We have flex suppressors, introduced an aluminum polymer for harsh environment, an exciting electroactive polymer actuator, large current power inductors, and surface mount radial crown aluminum electrolytic. So we'll get into each of those. And as I do, I just want to remind everybody of who exactly I am. As I said, my name is Wilmer Companioni, and I lead the technical marketing efforts at KEMET. I've been with KEMET in the technical marketing department for the last 7 years. And prior to that, have experience in design and in sales. So let's get into our first one, and that's our flex suppressors. So imagine a situation where you have a PCB with an EMI aggressor, and then right next to it is a victim of some descent. And inside of this is all contained inside of a metal enclosure. Now, when that aggressor starts to emit EMI, it can actually reflect off of the inside of the enclosure and affect other parts of the circuit. And flex suppressors are actually specifically designed to mitigate this situation. When you place a flex suppressor on the inside of the metal enclosure, it actually absorbs some of that some of that emitted EMI and prevents it from reflecting, or really attenuates the amount of EMI reflection you have that's attacking your victim here. Now, what happens inside of a flex suppressor, it actually takes that RF energy and converts it to a small amount of heat. Nothing that you can really feel or sense or is going to cause any excessive undue heating to your device that might affect the user at the ultimate on the other side of it. But still, law of conservation of energy, that EMI, that electromagnetic energy has to go somewhere. And the flex suppressor is actually made up of, imagine almost like tiny flakes of ferrite magnetic material suspended in a polymer elastomer so that it gives it that flexibility. So it's almost like a bunch of little pancakes stacked and dispersed throughout the material. And that's how it works. So, and the operating frequency for these things is up to 40 gigahertz. So that's where, for some of these newer technologies that we have coming out right now, particularly 5G and even Wi-Fi 6 and things like that, these flex suppressors can start to absorb and attenuate any undue and unwanted noise that are emitted by those new communication technologies. But there are some things to know about these flex suppressors. So first of all, for the right specific opportunity, they're going to be die cut into custom shapes. They don't have to be grounded like copper. If you imagine copper as an RF shield, it generally has to be grounded in order to do some attenuation. They are reflow capable. Now, like I said, they're not, you don't necessarily have to ground them. You shouldn't ground them, but they are, you can send them through reflow as long as you follow the right profile. And one thing to note is that they're not quite shields, and they're not shields in the sense that you would think of it. One of those reasons is that flex suppressors exhibit what's called anisotropic permeability, which means that the magnetic permeability in one direction is different than in the other direction. So as you can see here, when the field is transversing in a sort of parallel direction to the layout of the internal metal flakes, that has much higher permeability, much higher attenuation. than if you're going perpendicular to it. So on the simulation on the right, you can see that when you have free space, sort of an uncovered, untreated transmitter and receiver situation, the field expands all throughout, radiating out from the transmitter. And then if you were to put a metal enclosure or material on top of that, some of that radiated noise can couple along that metal enclosure and actually affect the receiver more. And then when you apply your flex suppressor, that's akin to the situation that I opened the presentation with, that it absorbs some of that and prevents it from getting to the receiver or the desense victim. Now there's another use case for flex suppressors, and that's the near field communication use case. So similarly, when you have a coil of wire, this is looking at the cross section, you have an antenna that radiates in all directions, and a receiver, in this case an RFID tag, trying to pick that up. You don't want that flux going, quote, behind the antenna, because that's kind of wasted flux, right? Wasted energy. And not only is it wasted, it can affect other things in the circuit. So what people do to prevent that is you put a piece of metal or sometimes ferrite behind it to try to absorb, well, to try to redirect some of that flux in the other direction toward the receiver. But then there's something we can do to actually improve that. And that's where the flex suppressor that we have that's specifically tuned for NFC frequencies, that's where that comes in. And if you place that between the metal backing and the transmitting antenna, as you can see from that simulation, you actually get more field coupling to the RFID tag, which can help improve distance sensitivity and things like that. So the flex suppressor is not just an absorber for unwanted EMI. It can actually help in the cases of RFID and even in cases of wireless charging. So now let's take a look at another one of the products that we've launched recently. That's what we call our A798 aluminum polymer for harsh environment. So aluminum polymer is not necessarily something new. We've had an aluminum polymer for a number of years. And the way that that's different than tantalum polymers, one of the core key products for KEMET, is that the anode material in this case is aluminum instead of obviously tantalum. Now there are some pros and cons and some benefits to going with aluminum as opposed to tantalum, but they are almost manufactured entirely differently, as you can imagine. So when in the case of tantalum polymer, you have a slug of sintered tantalum powder with a dielectric layer grown on it. In this case, it's actually more like little sheets, almost imagine little sandwiches of aluminum all stacked inside of an epoxy casing. So let's take a look inside of it and see what that looks like. So you have a core aluminum anode, and on that is etched a very, very high surface area, almost porous nature of it. And you grow an oxide dielectric on it, in this case, obviously aluminum oxide. And then you apply a conductive polymer cathode, and that's one single aluminum polymer element. And then you start stacking those, and you get a high degree of capacitance. So that's in a nutshell what aluminum polymer is. Now, what's different between this launch and recent launches of aluminum polymer is that this is actually capable of harsh environments. So we can go up to higher temperatures and harsher conditions that require more reliability than past the launches up to 125. So some of the comparisons between aluminum and tantalum is they're listed on the screen. Now the dielectric constant of aluminum oxide is lower than that of tantalum. So, by the very nature of it, you do get less capacitance. But one of the things to note that's a really positive for aluminum polymer is the very low resistivity of the anode material. So the very low resistivity of aluminum, it's about what is that, maybe 5 times less than that of tantalum. So these very, very low levels of ESR that you can get from aluminum, that's in part due to that very low resistivity of aluminum. And you can find these things for use in situations that you need elevated levels of reliability and uptime. So things like industrial automation, where these systems are sometimes operating continuously and sometimes unmonitored for many, many hours, weeks, days at a time, that downtime costs money, as it usually does. So that's one of the places where this A798 for harsh environment really excels, as well as computing systems and telecom systems, particularly as we start getting into the areas of 5G and these very, very small cells that are sometimes placed in somewhat inaccessible situations. So moving along, we have also introduced something pretty exciting, our electroactive polymer actuators. So as you can see in the little video on the screen, this is actually a very thin actuator that is almost akin to piezoelectric actuators. Now they're different in the sense that it's obviously an entirely different material set and different mechanical properties, but you will apply a waveform to it and they start to vibrate. A typical driver circuit includes a microcontroller with some sort of high voltage amplifier and then a feedback loop. And then you put through that different waveforms that can be used to deliver different sensations. And these things are meant to be embedded onto flexible and rigid substrates so that you can get tactile feedback fairly easily. As it compares to other haptic technologies, you have your classic ceramic piezo plates and discs that are pretty big and clunky and cumbersome. And the same applies to linear resonant actuators they can be decently small, but still consume a lot of space. And of course, your eccentric rotating masses, right? The things that we have in all our cell phones to give you that vibrating effect. And they're not very controllable in a sense. You can't create the same wide range of sensations with these classic technologies as you can with something like the electroactive polymer actuator. And they're actually also capable to be used in battery-powered devices. Now, we have done some studies, and in the use case here with a 2000 milliamp hour battery, with various different effects, you can see that it consumes a relatively small percentage of the overall battery capacity. And as I mentioned, they can be embedded into flexible applications, such as the fingertips on gloves or something like that, or even a rigid substrate like controllers for various devices. And then moving on to our large current power inductors. Now, what's interesting, I always find this interesting about these inductors. I always think about inductors as a coil of wire. And these inductors are actually not that. We call these, internally, sometimes we refer to them as our single turn inductors, in that it basically just has a straight connection between the pins, and then that's all sandwiched inside of a ferrite core, of ferrite material. Now, what that enables is you can, because of the relatively high permeability of that ferrite material, you can get a fairly high amount of inductance from that one turn. And what that one turn also does for you is that it has very low DCR. Because if you think of the resistivity equation, which is R is equal to rho L over A, when you minimize the overall length of the conductor, you minimize the overall the total resistance. So you have a low DCR, which is what enables some of those high currents that I have highlighted there on the screen, 36 up to 53 amps. So how it compares to other inductor technologies, you have generally, for really high current applications, you have two sort of alternative solutions. You have your metal composite inductors, which is what we call our METCOM series, and then you have these ferrite inductors. So just like there's no one perfect capacitor, there's no one perfect inductor. And in the case of the ferrite inductors, they have a high level of inductance, but a much harder saturation profile. And what this latest release of these large current power inductors have done is to push that saturation point, that this cliff where it falls off, to push that further and further out so you can get those high currents. Now, power inductors have a much softer saturation profile, but their cores are inherently lossier, especially at the 1 to 2 megahertz range, which is where a lot of new DC to DC power converters are going. And speaking of DC to DC converters, that's exactly where these are really tuned for, and where these are going, to DC to DC power converters, including resonant converter applications, where you're trying to push up those frequencies to get into that really highly efficient area. And as with everything else, the purpose of this is to all try to shrink it down and get things, pack more electronics into different systems. So in the case of something like a VRM or a power distribution network in digital devices, you want to get those as close to their destination as possible to minimize the amount of ohmic losses throughout the circuit path. And finally, the last launch I want to talk about is our SMD radial crown aluminum electrolytic. Now, that's a mouthful, and I'll get into what this is and why they're interesting. So as you can see, they come in two different configurations. Now, these capacitors are actually the SMD variant of a very successful aluminum electrolytic series that we have, which are through-hole version, that have found a lot of success in the automotive space, areas where you have you require a lot of ripple current performance. And as you can see, these are capable of temperature humidity bias situations of up to 2,000 hours at 85 degrees C, 85% relative humidity, up to 2,000 hours. So essentially what we're bringing now with this surface mount configuration is the success of that previous through-hole implementation, but now in a surface mount package. So as I said, you can find those in automotive applications, definitely DC links and on the other side of inverters. So with that, I think, okay. So that's all I wanted to cover today as far as our first quarter product launch retrospective. And now I'll open it up to some questions, if there are any. If there are no questions, you can, then as you exit the webinar, please take our post-webinar survey so that we may improve this experience for the audience. And if you have any questions that come to you after the fact, you can follow the link on the screen, and we will be sharing this presentation with you in a short amount of time. So with that, I'll wait a couple of seconds for some questions to come in, and if there are none, then we'll adjourn. All right. Well, it looks like we have no questions, so thank you everybody for attending, and we'll see you at our next webinar in 2 weeks. So thank you very much.